coming to the types of HDLs, there are two popular types of HDL. One is the VHDL and the other one is the Verilog. Over here we shall be studying Verilog. And using Verilog, one can design, simulate and synthesize. We have understood what we really mean by design, analysis and synthesis. So using this Verilog, we can check whether the hardware modules are concurrent or not, whether the timing behavior is met or not, and it can also handle asynchronous as well as synchronous sequential logic designs. So that varies from, in fact, country to country. If you see the European countries, their Verilog is more popular. If you see the American or even in Australia also, VHDL is very popular. British, they use Verilog. In India, again, it's a mixture of Verilog and VHDL. So there are some companies which are too much reliant on this Verilog, some companies too much reliant on VHDL. But in actuality, if you learn one language, it is not really difficult to learn the other languages, because the features remains almost the same from one language to another. So to depict the role of HDLs from Gajeski's Y chart, we start with an so it basically depicts the spiral model of digital design flow. So we start with an algorithmic description of the system, we translate it into the interfaces of the processors at the structural level, and then we give a board level description at the physical level. Then we express these algorithms as an in terms of register transfers, which means we exist at the RT level, which we translate it into registers at the structural level, and then translate it into in terms of chips. And then below the register transfer level, we have the gate level, for which in the behavioral dimension we express it as in terms of Boolean equations, and in terms of structural level we express it as an interconnection of gates. So that is how the spiral model keeps on flowing. Ultimately you arrive at the intersection of these three dimensions. So that actually again leads to rapid prototyping of the system. So while a team of people are basically translating a description from one domain into another team can start the next iteration. That really leads to an increased speed in the design flow process. However, you need a large team to implement the notion behind this Gajeski's Y chart. So if you look into the behavior of analyzing the circuits with the help of hardware description languages, we use a stimulus generator to provide certain inputs to the circuit under design and check the outputs of the circuit. So we use a test bench to generate the stimuli for the circuit under test and check the output. So looking at the basic structure of a Verilog program, the main module is called, so this module is basically the unit of a Verilog program. It contains the description of individual components. So a module begins by the keyword followed by the name of the module, and then you give a list of the ports, the various declarations, and then you give a functional specification or a description of the module, and finally it should end with end module. So these are the various components of a typical Verilog module. So in this 2-to-1 multiplexer, we are defining the module marks 2 and then defining its interfaces. This so we define the output interface followed by the input interfaces, but it is no such hard and fast rule is there that you have to specify the output interface first followed by the input interfaces. You can do it in any sequence, and then we are specifying which one is the output interface, which ones are the input interfaces, and then we come to the description of it. So over here we are basically having an event driven modeling of the system, which means that if any event occurs in the inputs in1 or in2 or select, then that will be reflected at the output. So this is the always syntax we use for that purpose. You can also use assign. So in the tutorial classes you will be taught the details of these syntaxes. Now this is very important to know the different styles of modeling we use in a hardware description language. By styles of modeling we mean that the direction from which we look into a hardware. We have to, so our notion of the hardware is very hazy and abstract, and we have to translate our hazy abstract idea of the hardware into some concrete description by means of hardware description language. So we have to depict that in terms of some modeling. Traditionally there are three styles of modeling: the structural modeling, behavioral modeling, and data flow modeling. In case of structural modeling, we basically depict the system as an interconnection of its lower level components. In case of behavioral modeling, we depict the behavior of the system without any regard to its interconnections in it. And in case of data flow modeling, we visualize the system as a data flow graph. What are the processing nodes in it and so on. So looking at the example of this half adder, we can, if you just look at the half adder without any regard to the details of what is there inside it, it is basically a circuit with two input interfaces, two output interfaces. So the output interfaces we call it, we give the name S and C, and input interfaces we give the name A and B. So that basically defines the external interfaces of this half adder. Now coming to the functional description part of it, if it is a data flow style of modeling, then we visualize it as a collection of two nodes, one of which is computing the XOR of the two inputs, the other computing the AND of two inputs. So we depict the half adder as a data flow graph, and that is translated in this way into a code for the half adder. Coming to the behavioral modeling of the half adder, we are looking into the same half adder from a functional perspective, which means we are not referring to its interconnection of components or looking into the half adder from as a collection of some computing nodes or so. We are looking at the flowchart of the half adder. We are inputting to these two inputs A and B, and then checking one input. If one input is equal to 0, then we are checking the other input. If it is also equal to 0, then the sum is 0 and carry is 0. If one input is not equal to 0, that means it is equal to 1, then we are checking whether the other input is equal to 0 or not. If the other input is equal to 0, then the sum is 1, carry is 0, otherwise sum is 0, carry is 1. So if you think a little bit, we are basically implementing the truth table of the half adder through these lines of codes. So given any truth table or a state table, we can implement any digital circuit. So that is what we had. So we can understand that a truth table or a state table basically depicts the behavior of a digital circuit, and that is what we are doing through these lines of codes. Only one thing I need to say over here is that we are using this always at syntax, so that we are having an event driven modeling of the system, so that if any event occurs in, that means any change occurs in this inputs A or B, that is reflected at the output. Coming to looking into the same half adder as an interconnection of its lower level components, we are looking into the same half adder as an interconnection of XOR and AND gates. So we are creating instances of the XOR gate as well as the AND gate, and mapping the interfaces of the XOR gate and the AND gate in terms of interfaces of the half adder. We may also do, in case of practical systems, we may also do structural modeling for some part of the design, behavioral modeling for some other part of the design, or data flow modeling for yet another part of the design. So that is what we really mean by mixed style of modeling. So going to the example of a single bit multiplexer, this is basically the Boolean equation for the 2-to-1 multiplexer. If you visualize the 2-to-1 multiplexer from a structural perspective, then you can visualize the multiplexer as an interconnection of these AND, OR, and NOT gates, and then you can write a netlist depicting the interconnection of the logic gates. That's what we are doing over here. So this half adder is basically a set comprises of a set of 2 AND gates, 1 OR gate, and 1 NOT gate, and that's what we are instantiating over here. We are instantiating 1 NOT gate, 2 AND gates, and 1 OR gate, and defining the interfaces of the NOT gate, AND gates, and the OR gate in terms of the interfaces of the 2-to-1 multiplexer. So if you define that, if you see the 2-to-1 multiplexer, we are defining